Dear participants of online certificate program on sustainable materials and technologies, a pleasant morning to you all. Myself, Dr. A. Sambat Kumar, Assistant Professor of Chemistry, Vivekananda College of Arts and Sciences for Women, Autonomous, Tiruchengode, Namakkal District. It's my pleasure and privilege to discuss about solar energy conversion devices, which comes under Unit 5 of our course layout. And in this presentation, we have two parts. Part 1 consisting of dye-sensitized solar cells and another part consisting of perovskite solar cells. And let me discuss one by one. And before going to talk about the topic solar energy conversion devices, I would like to give you a message during this lockdown period for our safety. Stay home, stay healthy. With this message, I will move on to the presentation. Before going to talk about the solar energy conversion materials, that is dye-sensitized solar cells and perovskite solar cells, I would like to explain about sustainability in brief. And you might have studied in the previous units about sustainability in detail. And here I would like to correlate the sustainability and their impact, sustainability and its impact with the devices, that is solar energy conversion devices. First, what is meant by sustainability? Sustainability, which is nothing but sustainability is based on simple principle. We can define whatever we required for our survival, either directly or indirectly, in our environment is called sustainability, which has impact on society, environment and economical aspects. Whatever may be the invention, if the invention considered to be a promising one, in the sense which should have an impact on social, environmental and economical aspects. So these three aspects are very important for any inventions to become a high utility. So our dye-sensitized solar cells and perovskite solar cells has those impacts, that is social, environmental and economical aspects. Hence, the solar energy conversion devices also considered as a sustainable energy devices. Hence, they have social, environmental and economical impacts, which is the prime advantages of them. So the devices are also called as sustainable energy devices. So there is a correlation between sustainability and the devices has been proved here. And with this brief introduction about sustainability and its relevantness with solar energy conversion devices, I will move on to the part 1, dye-sensitized solar cells, where we will discuss about the design, that is design of sensitizers and components, various components present in dye-sensitized solar cells, and the working principle, that is mechanism of dye-sensitized solar cells. First, we see about need and importance of dye-sensitized solar cells. Need in the sense why we require dye-sensitized solar cell and what is the necessity and why it is so important. Those things will be discussed. Energy demands and environmental issues such as global warming have led to the search for clean energy sources in recent years. In other words, currently available fossil fuel resources are limited and depleted rapidly during the recent decades. Hence, there is an increasing global awareness concerning the crisis to find alternative renewable energy sources such as solar energy to meet the requirements and developments of modern society. So, moreover, the solar energy is abundant in nature, free from sun. So, in order to capturing sunlight and converting them into electricity, we required certain device. So far, many researchers have proposed many devices for capturing solar energy and converting them into electricity. And among the proposed devices so far, dye-sensitized solar cells and perovskite solar cells are attracting widespread interest because of their extraordinary advantages, that is low cost and high molar extinction coefficient and high performance, that is efficiency, and also which is eco-friendly in nature. These devices, solar energy conversion devices, especially dye-sensitized solar cells and perovskite solar cells, comes under the category of third generation solar cells. Initially, Professor Dr. Michael Gratzel who is a well-known scientist across the globe, still is alive, from EPFL, Switzerland. He has worked in dye-sensitive solar cell. He has constructed dye-sensitive solar cells initially by using ruthenium polypyrrole complexes with the titanium dioxide semiconductor nanomaterial and achieved 7% efficiency, and later he got 11% efficiency. And for his invention he got awarded Millennium Technology Prize 2010, which is a prime award across the globe. And later the dye-sensitive solar cells, also called as great cell cells, since father of dye-sensitive solar cell is Professor Dr. Michael Gratzel. And due to the precise of metal and its rarity, and also the toughness of the preparation procedures for metal complexes, people have considered metal-free organic dyes as a promising candidate for dye-sensitive solar cells and for practical applications. And that's about the need and importance of dye-sensitive solar cells. And so far we have achieved 14.3% of efficiency, that is photon conversion efficiency, by using metal-free organic dyes in dye-sensitive solar cells. And components of dye-sensitive solar cells: the dye-sensitive solar cell device consisting of the essential 4 components. One is semiconducting electrode, that is anode. And normally people have used titanium dioxide, since which has advantages when compared to other materials like nickel oxide, zinc oxide. Later the semiconducting electrode, that is anode, coated with dye sensitizer, that is dye molecule. It may called as photoanode. And then dye sensitizer, which should have absorption in the visible region. Since semiconducting electrode does not have absorption capacity of visible light, which the semiconducting electrode have absorption in the range of UV only, that is 200 to 400 nanometer. Hence we required on dye molecule which should have a visible absorbing capacity. That is since sunlight is visible light, that is solar energy is visible light. So in order to capturing solar energy, semiconductor electrode can't get solar energy directly. So to sensitize the surface of semiconducting material, we use dye sensitizer, or we coated dye sensitizers to capture the visible light, that is sunlight, which should have a light where the light harvesting and electron transitions occurred. And redox mediator, that is electrolyte, normally iodide triiodide redox couple have used widely instead of all other metal complexes and other electrolytes. Then counter electrode, that is cathode, normally which may be a carbon or platinum, used as a counter electrode. And these 4 components are considered as an essential component for dye-sensitive solar cells. And among the proposed components, dye sensitizers plays an important role in the aspects of efficiency, that is performance of the device. So what makes a good solar photovoltaic material, that is what is the criteria for the materials to be promising as a sensitizer for dye sensitive solar cells, is high photon capture cross section in the UV and visible region, that is the material should have high visible absorbing capacity, that is 400 to 800 nanometer absorption should be required. And efficient production of photo-excited charges, that is while eliminating the light, that is sunlight, upon eliminating sunlight to the dye sensitizer, we should have inject electrons, that is photo-excited charges. Then efficient transfer of photo-excited charges to some external circuit, that is able to be integrated in a suitable photovoltaic device platform, that is the injected electrons move towards the conduction band of titanium dioxide, that is semiconductor material. And the material should be cheap, biocompatible, preferably bioavailable, processable, stable both chemically and photochemically. Then the LUMO of the sensitizer, that is the LUMO of the sensitizer, that is the reduction potential, may consider as a LUMO of the sensitizer is more negative than conduction band of TiO2, which is localized from which is localized from acceptor, and the HOMO of the sensitizer is more positive than electrolyte. That is HOMO in the sense oxidation potential. HOMO is mainly localized, should be mainly localized in the donor part, which is electron rich. These condition will ensure the promisingness of the material for dye-sensitized solar cells. Since these condition will satisfy the efficient electron injection and dye regeneration, which is very very important for material for sensitizer for being a promising candidate in dye-sensitized solar cells. So the LUMO of the sensitizer is more negative than conduction band of TiO2, and the HOMO of the sensitizer is more positive than electrolyte for efficient electron injection and dye regeneration, and that can be calculated from photophysical properties as well as electrochemical properties. And normally in metal free organic dyes, donor by acceptor push-pull character is a general one. So here we may see the donor by acceptor organic dyes anchor and TiO2 surface, which is a typical organic architecture where the donor gets illuminated by sunlight, that is which get absorbs photons from the sunlight, where the electrons push towards the acceptor, where the acceptor gets electrons from the donor via pi spacer, then the acceptor pulls the electrons from the donor. Since acceptor is electron withdrawing in nature, donor is electron rich normally, so the acceptor has a tendency to absorb on TiO2 surface, that is surface of TiO2, that is which can have a capacity to anchor on the surface of TiO2, where the electron injection takes place from the excited dye. This is a donor by acceptor push-pull organic. That's about the donor by acceptor push-pull organic architecture. Normally many donors so far have been scrutinized by many researchers, and among them triphenylamine phenothiazine and carbazole are considered as a promising donor material. And spacer, for example of some of the spacers are furan, thiophene and phenyl ring. And acceptors, cyanoacetic acid, rhodanine moiety and nitrophenyl isonitrile are well-known acceptors in the case of dye-sensitized solar cells, that is in the donor by acceptor push-pull organic sensitizers. So normally a donor should be rich in electron, acceptor should have a electron withdrawing nature, and spacer which has highest double bond, that is conjugation. So those things are considered for a material to becoming a good material for photovoltaic aspects. And though donor by acceptor traditional organic architecture, that is the push-pull architecture, is much interest, by introducing additional donor to them, that is secondary donor or auxiliary donor into traditional T by A architecture, the molecule gets starburst structure, that is the donor by acceptor structure, or DD by A or D2 by A structure, which avoids charge recombination process between injected electrons and electrolyte, which will enhance the efficiency of the device and extend the visible region, that is extend the visible absorbing region, and enhance the intramolecular charge transfer via pi stacking, which will enhance the photocurrent. So automatically the efficiency of the device will increase. Some of the examples of additional donors are imidazole and benzimidazole derivatives, phenyl derivatives, and so on. And anchoring group not only participate in anchoring of the electrons, that is anchoring of surface of TiO2, which should have a capacity or which is responsible for photophysical properties, electrochemical properties, as well as the photovoltaic performance of the dyes. So the design of the sensitizer based on donor or donor by acceptor dye, the design is very important. While designing the molecule, the things which we discussed is to be considered much. Then working principles of dye-sensitized solar cells, that is basic mechanism of dye-sensitized solar cells. The mechanism shown here as a pictorial representation, where the dyes gets light, that is absorbed photons from sunlight, then the dye get oxidized, that is it goes excited state where the photo excited electrons injected. The injected electrons moved towards the conduction band of titanium dioxide nanomaterial, that is a working electrode or photoanode. The working electrode transfers the electrons to the counter electrode, that is platinum or carbon, via the external circuit, where the counter electrode transfers electrons to the redox mediator. The redox, where the oxidation and reduction takes place. The redox mediator donate an electron to the oxidized dye. Then the oxidized dye gets reduced and comes to the natural comes to the original state, that is neutral state. Then again and again the cycle is flowing or repeated until the dye is stable. That is the dye in the aspects of quantum yield is considered here for stability. So high quantum yield is in the sense the dye should have a high stable, which will have a long life period for these applications, that is dye-sensitized solar cells. And that's about the mechanism of dye-sensitized solar cells, that is working principles of dye-sensitized solar cells. And I hope we'll move on part 2 with this brief introduction of dye-sensitized solar cells. Now I will move on to part 2, that is perovskite solar cells. Here we will discuss about the structure, components and mechanism of perovskite solar cells. Perovskite structure. Perovskite is any mineral which has AbX3 crystal structure. A and B are two cations of varying sizes, that is very different sizes, and X is an anion that bonds to both. So normally perovskite solar cells stem from dye-sensitized solar cells, that is the perovskite solar cells derived from dye-sensitized solar cells, and which is also a third generation solar cells, and most common type of crystal structure for calcium titanate, which is also a well-known perovskite structure, which has a cubic lattice nested octahedral layered structure and the unique optical, thermal and electromagnetic as well as electrochemical properties, which have a high future potential, that is photon conversion efficiency boomed up to 20%. Perovskite solar cells is derived from the AbX3 crystal structure of the absorber material. So perovskite material is also called as absorber material in the case of perovskite solar cells, and most common perovskite absorber is methylammonium lead halide. In that methylammonium lead halide, methylammonium lead iodide is most commonly used material for making high efficiency perovskite solar cells, which is a type of organometal halide crystalline system of perovskites, and which has a more advantage as like in dye-sensitized solar cells, which is low cost and high efficiency. So far 22.1% of efficiency have been achieved by using perovskite material in a planar structure. The perovskite material can be used not only as a light absorbing layer, that is absorber, but also an electron or hole transporting layer due to the advantages of its high molar extension coefficient and high charge mobility, low carrier lifetime and longer carrier diffusion distance. And that's about the perovskite structure. And let me move on to the device structure of perovskite solar cells. The perovskite solar cell device structure related to material and interfacial modification are key factors in performance of solar cells, which is pictorially represented here. The two typical structure can be constructed. Mesoscopic nanostructure, which is mesoporous titanium dioxide layer, is usually used to collect the electrons, which shows in figure A. An organic hole transporting material, that is planar structure, organic hole transporting material HTM, which collects holes, and planar structure has simpler structure and high efficiency, which is shown in the corresponding structure exhibits here. And components and working principles of perovskite solar cells. The components are same most probably as like in the case of dye-sensitized solar cells, except electrolyte. Since in the case of perovskite electrolyte there is since in the case of perovskite solar cells there is no electrolyte have been used. So the important components of perovskite solar cells are metal electrode, probably cold, and hole transporting layer, probably a spiro compound, and organic heterocycles also be used as a whole transporting layer, and absorber layer is methyl ammonium lead halide, and some of the possible absorber layers are mentioned here for your reference. And electron transport layer, normally titanium dioxide semiconducting nanomaterial. So that's about the components. These are all considered as essential components in the perovskite solar cells, and the working principles of perovskite solar cells. In the left, bottom left, the picture that is the figure shows the perovskite layer. That is the perovskite solar cells structured layer, where the perovskites, whole transporting material, and electron transporting material, and ITO plate, and so on, we can clearly observe here. And the right bottom, we have the mechanism of perovskite solar cells, that is working principles of perovskite solar cells, where during the exposure of sunlight, the perovskite layer firstly absorbs photon to produce excitons, that is electron hole pairs. Due to the difference in exciton binding energy of the perovskite materials, these excitons can form free electrons, free carriers, free electrons and holes to generate a current, or can recombine into excitons. That's about the principles of, that is working principles of perovskite solar cells. And I hope this will be enough for the better understanding of both dye solar cells and perovskite solar cells. I don't want to go much deeper in those topics, and I have highlighted few important things only here, and the detailed content for your better understanding. We have uploaded the detailed content in our Google Classroom, that is our online certificate program on social materials and technologies classroom. We have uploaded the detailed content of the topics dye solar cells and perovskite solar cells. We have uploaded, where you can have a detailed content. Here I just wanted to give you key points only, that is why I have highlighted the important things here. And finally, I would like to give you a message regarding sustainability, so which is very important for us, so which is a take home message: go green, save earth, save our life for our future generations. And with this message, I would like to conclude my session. If you have any questions or queries, please write via Dr. sampathkumar@vikas.org. Thank you for your kind attention, and once again I thank you one and all for your kind attention.